Positions. We don't tend to think much about it throughout our day-to-day lives. However, positioning can have a great effect on outcomes. Let's use a subject everyone loves to translate my point, chemistry. There exists a phenomenon known as chirality. This simply means that two molecules that are mirror images of one another cannot be superimposed. So if you were to take one and place it over the other and try to place them exactly the same way, that would be impossible. Let's view this topic from a more macroscopic standpoint. If you can, take your left hand and your right one and let your palms face the ceiling. Now, try to place your left hand over your right one. What should result is that the two hands cannot perfectly be placed over one another. Your thumbs stick out at opposite ends and your fingers do not correspond with one another. The only exception is the middle finger. This same logic applies to molecules when they have a stereocenter. Stereocenters or stereogenic centers are used to describe locations on a molecule where a carbon atom has four different elements or compounds attached to it. The middle compound does not necessarily have to be a carbon, but this is often the case. So in the middle of these two compounds here, imagine a carbon atom. In organic chemistry, they don't have to be shown, but there is a carbon atom right here in between all these four. We have to remember that when looking at a molecule, some of the elements may be coming at you in space, or they may be going away from you. We have to visualize it in a 3D space because many stereocenters elicit tetrahedral geometry. There are exceptions where molecules that do not have tetrahedral shape can also be chiral. Nevertheless, we will focus on those that are tetrahedral to simplify the concept. The 3D structure of a molecule is illustrated by dash and wedge bonds. Wedge bonds mean the element is pointing away from us in space, and dash bonds mean the element is pointing towards us in space. Now that we have a basic understanding of chirality, stereocenters, and 3D structures, let me introduce the importance of positioning in chemistry. Stereocenters allow us to determine whether a molecule is rectus or sinister in nature. No, I do not mean that type of sinister where the molecule is a ghost and will haunt somebody. This sinister is the Latin word for left, and rectus is the Latin word for right. The way this configuration is determined is by the priority of the elements surrounding the carbon atom in the stereocenter. Priority is given to elements that have a higher atomic number. This number can be viewed on the top of elements in the periodic table. There is also one more rule that is important to note. We want the bond pointing away from us, which is referenced by the wedge bond, as mentioned previously, to be the one with the lowest atomic number. The issue is that if the element with the lowest atomic number is pointing towards us, then the configuration becomes switched and what was originally R becomes S and vice versa. So I'll be referencing rectus as R, so towards the right, and sinister as S, so towards the left. There are many other technicalities I will not go over, but this should be enough to understand what I am about to show. So for this example, let's look at ibuprofen, which is also known as Advil. So many of you may be familiar with this type of medication. Ibuprofen is a drug typically used to reduce fevers or treat different forms of pain, so it's referred to as an analgesic drug as well. Don't be alarmed by the structures, but this is the chemical structure of ibuprofen. We're going to narrow in mostly into this area right here, where I've drawn the dash and the wedge bonds. To begin, the first thing we notice is that there exist two configurations. We have R-ibuprofen and S-ibuprofen as well. First, let me prove why the first one is R-ibuprofen. So we have this carboxylic group over here all the way to the right. This would be the first priority. I won't get into the technicalities of why, but this one would be the first one. This carbon that is double bonded here would be second priority. The methyl group, which is the CH3, will be third, and the hydrogen will be fourth. So this is good. We have the lowest atomic number, which is the hydrogen, all the way towards the back, which is indicated by the wedge bond. So if we were to look at the order to go to determine the configuration, we see that it goes 1, 2, 3, 4. So it would go towards the right motion. So it's R-ibuprofen. Now for S-ibuprofen, same thing in the start. So this carboxylic group has first priority. Then we have this double bonded carbon over here second. Then the methyl group is third, then fourth. The thing is that the lowest priority group, which is the hydrogen, is coming towards us. And since it's coming towards us, we want the lowest priority group to be all the way towards the back. This means that we have to adjust the molecule, but obviously this is in a 2D space, so we can't really adjust it. You'd have to adjust it with the molecular kit or kind of try to imagine it and envision it in your mind. But there is a simple rule where if the lowest priority group is facing forward, we could simply just switch the configuration. So originally this would be R, 1, 2, 3, 4, as you can see. Since it's R, once you do change around the molecule and put the hydrogen all the way towards the back, since it's the lower priority group, then it flips around and it actually becomes S. Hence why it's S-ibuprofen. What is interesting is that the position of the methyl group shown and the hydrogen completely alter the way that this molecule functions. S-ibuprofen turns out to be the one with anti-inflammatory properties. R-ibuprofen does not show these effects. Thus, position is a crucial detail in something as small as molecules. It should be noted that a molecule and its chiral counterpart have the same physical properties. That is, some of their characteristics, such as melting point, boiling points, they're the same. Yet, a subtle change in the position of these two bonds can completely alter the way a molecule functions. Now, I know you're all going to hate me for this, but let's move away from chemistry. It's time for us to move on to optical illusions. Take for instance the Zöllner illusion, which was devised by a German astrophysicist known as Johann Carl Friedrich Zöllner. The way this illusion works is that the vertical lines appear to be slanted. This is in fact not the case. These vertical lines are parallel to one another. However, the positioning of the diagonal lines makes it seem as if these parallel lines will intersect at one point. We do not yet have a clear understanding of why the lines appear to be slanted, but contemporary reasoning uses the acute angle expansion hypothesis. It states that perception systems in our brains accentuate acute angles and undervalue obtuse angles. If you squint when looking at the image, the lines are seen as parallel. These diagonal lines appear to fade away as we squint, which, in turn, removes the acute and obtuse angles that were previously present, hence why we're able to see them as parallel. The acute angle expansion hypothesis has one piece of convincing supporting evidence. Once the vertical lines are replaced with squares that would form a parallel line, it appears that the image is no longer distorted. So we can deduce that the position of these diagonal lines and vertical lines is key to producing the illusionary effect of the image. The importance of position does not only apply to matters in chemistry and illusions, it can also be observed in everyday instances. Take a courtroom, for example. Several cases are viewed each day, and courtrooms tend to have a similar layout. Firstly, take a look at the positioning of the jury relative to the dock. The jury, which is visible all the way to the left of the image, is facing the dock head on. The dock is shown all the way to the right of the image, and it is the space where the defendant or the accused will sit. The position allows for the tribunal effect to settle in as the jury feels the weight of the situation on their shoulders. They will eventually decide if this person is guilty or not guilty for the crimes or crime presented. Another feature of the courtroom that is important to note is the position of the judge relative to everyone else. This feature alone resembles the authoritative power of the judge within the courtroom. Often, they are the ones to decide the ruling of a case, so it makes sense why they must overlook everything in the courtroom. There is more than meets the eye when viewing where something is situated. Think about yourself and the events that have unfolded in your life. All this is due to your position.